Let's try to have a look at what happens to the kinetic energies. And for this purpose, what I've taken is this 3D coordinate system that you've seen before, and there are masses m1, m2, m3 placed at r1, r2, r3 and so on, moving with velocities v1, v2, v3 and so on. And all these, I should again emphasize, are from the ground frame or from this O frame. So in this origin frame here, the masses are placed at r1, r2, r3 and so on at all those locations, and the velocities are v1, v2, v3 and so on up to vn, while the center of mass itself has a location r center of mass and has got a velocity v center of mass. So let us try to figure out what will be the relation between this velocity v3 and let us say v center of mass, or maybe v2 and v center of mass, or maybe v1 and then v center of mass or something. So you know that v1, and of course because these are from the ground frame, what I will be doing is I will be using the subscript with respect to ground. So what I can do here is I can put a slash and I can put g, and for the v2 also I can put a slash and then put a g, and for the v3 guy also I can put a slash here and then put a g to emphasize that they are in the ground frame. So v1g, v2g and v3g, and after that vng are the velocities of all these n particles in the ground frame. So velocity of particle 1 in the ground frame is going to be velocity of particle 1 in the center of mass frame plus velocity of center of mass in the ground frame. You know that this is how we try to find the relative velocities. This is the law of addition of velocities. And in the same manner, we will have velocity of 2 in the ground frame is equal to velocity of 2 in the center of mass frame plus velocity of center of mass in the ground frame. Velocity of 3 in the ground frame is going to be velocity of 3 in the center of mass frame plus velocity of center of mass in the ground frame, and so on. So you will have expressions like this filling up the screen here, and I don't want to do that for n terms, so I will just finally say that for the nth term, velocity of nth particle in the ground frame or with respect to the ground is velocity of the nth particle in the center of mass frame plus velocity of center of mass in the ground frame. And because I will be doing everything in terms of vectors here, I think it will be good to recall some vector properties. So first is, you should recall that kinetic energy of a particle can be defined as half mv square, where small v is its speed and m is its mass, of course. V is its speed or the magnitude of velocity, right? And there is another way to write this result, and that is half m v vector dot v vector, where v vector is the velocity of the particle. So you can then easily recall that a dot b, so here it's v dot v, it will be magnitude of the first one into magnitude of the second one into cos of angle between these two, and the angle between these two is going to be 0, so cos of 0 is 1, so you're going to get back that expression. So half m v dot v, that is a very concise expression which I can use for the velocity for maybe a v square term, you know. So now what I want to do is I want to find out the kinetic energy of all these particles which are moving around in the ground frame. So kinetic energy of all the particles in the ground frame, kinetic energy of all particles in the ground frame, and what do I get? That will be kinetic energy of the first particle plus kinetic energy of the second particle plus kinetic energy of the third particle and so on. So maybe half m1 and velocity of 1 in the ground frame dot velocity of 1 in the ground frame plus half m2, and I'm going to have velocity of 2 in the ground frame dot velocity of 2 in the ground frame, plus so on. I will have n terms. No enthusiasm to write all those, no need to write all those, so I'm just going to put a series of dashes and asking, and I will just ask you to imagine that there are all those terms filled up. Half mn and velocity of nth particle in the ground frame dot velocity of nth particle in the ground frame. So this is what I end up with. Fine, this is the K of all the particles in the ground frame. Now, as you would have guessed, you will substitute for V1g here, and that will be V1 center of mass plus V1 with respect to center of mass plus velocity of center of mass with respect to ground. So let's only have a look at the first term here. What this first term will look like is velocity of 1 with respect to center of mass plus velocity of center of mass with respect to ground dot velocity of 1 with respect to center of mass plus velocity of center of mass with respect to ground. Okay, cool, no big deal. And then we can try to use the distributive property of dot product. So the first term dotted with the first term, then the first term dot with the second term dot with the first term, and the second term dot with the second term. So that's the sequence. So when the first term goes with the first term, you are going to end up with a V1 center of mass, V1 in the center of mass frame dot V1 in the center of mass frame. That will be V1 in the center of mass frame square, magnitude square, So the first term will become V1 with respect to the center of mass square. And I'm going to throw the vector sign on the top because it's a magnitude square. So this is this guy's magnitude times this guy's magnitude times cos of 0, and I've just got a magnitude square here. Plus, let me look at the last two terms. So V center of mass with respect to ground and V center of mass with respect to ground. So when I take their dot, it will be just this guy's magnitude times this guy's magnitude times cos of 0. So I'm going to end up with V center of mass with respect to ground square. Plus, now you know that it doesn't make a difference whether it's A dot B or B dot A, we get the same result. So V1 center of mass, V1 with respect to center of mass dot V center of mass with respect to ground, or V center of mass with respect to ground dot V1 center of mass, it's the same thing. So I'm going to end up with 2 V1 with respect to center of mass dot V center of mass with respect to ground. This is the last term. And this is the entire expression which I will get after opening it up. And I still have half and m1 outside. So when I try to bring in those terms also, so what does the first total term become? Let me just enclose it in some kind of a blue quadrilateral and show you what that becomes. It will become half of m1 times v1 with respect to center of mass whole square plus v center of mass with respect to ground whole square plus 2v1 center of mass dot v center of mass with respect to ground, and similar terms for all the other terms also. So I will have the second one open up as half. So here half is half. In place of m1 I will have m2. So half m2 v2 in the center of mass frame square plus v center of mass with respect to ground square plus 2 times of v2 with respect to center of mass dot v center of mass with respect to ground. So that's the second one, then the third one, and so on. So each of these terms will lead to 3 different terms. So if I've got n terms here, one for mass 1, one for mass 2, one for mass 3, and one for mass n, and so on. If I've got n terms here, after opening up each bracket and trying to write all of them in a summation fashion, I'm going to get 3 n terms. And what do I do with the 3 n terms? I club up the first term of each bracket. So this is equal to, and after I club up the first term of each bracket, it will be half m1 v1 with respect to center of mass square plus half m2 v2 with respect to center of mass whole square plus so on, and the last term will be half mn Vn with respect to the center of mass whole square plus. Then I will club up all the center terms in all the brackets. So half m1 V center of mass with respect to ground whole square, V center of mass with respect to ground whole square plus half m2 V center of mass with respect to ground whole square plus so on, so on, so on. The last term will be half mn V center of mass with respect to ground whole square plus. What will the third term give me? The third term is going to give me, see, there is a half here and there's a 2 there, they will cancel out. So m1 times, so I'm going to get, and this is important, so let me put that in red. I'm going to get m1 times v1 with respect to center of mass dot v center of mass with respect to ground. So please keep in mind that still I have not been able to do away with the dot product here because I don't know the angle between these two velocities. So I can't do much about this expression. The second term will be m2 v2 with respect to center of mass dot v center of mass with respect to ground plus, and so on, so on, so on, so on, and I'm going to end up with the last term, that is mn Vn with respect to center of mass dot v center of mass with respect to ground. Okay, cool. So what do the green brackets give me? So if you look at the first green bracket, that's the kinetic energy of all the masses in the center of mass frame, because what I'm doing is, standing in the center of mass frame, I am looking at what is the velocity of first particle and I am just finding out half mv square with that. Then standing in the center of mass frame, what is the velocity of the second particle and finding out half mv square with that. Then so on for all the n masses. So this is basically kinetic energy in center of mass frame. This is the first term. What does the second term give me? The second term, if you notice, there is a half in all those terms which will come out common. Then there is a V center of mass with respect to ground square in all those terms, that will also come out common. And what you will have is just m1 plus m2 plus m3 plus so on up to mn. So you are going to get half summation of m times V center of mass with respect to the ground whole square. And what does the last bracket give me? And this is the most interesting bit. So you will, I think, be easily able to guess what do I intend to do. So I see that there is a dot product in the first term, second term, third term, and so on for all the n terms. And then I invoke the distributive property of dot product. So I say that this entire term looks like, so this entire red encircled term looks like m1 v1 with respect to center of mass plus m2 v2 with respect to center of mass plus all that till mn vn with respect to center of mass dot v center of mass with respect to ground. Because if I just open up the entire dot product thing, if I try to distribute it, I'm going to get back the same expression which I have there. But then this expression is pretty interesting. You have seen it just now. So this expression is summation of mi vi with respect to center of mass. And this is the total linear momentum in the center of mass frame. So this term is the total linear momentum in the center of mass frame, people. Total linear momentum in the center of mass frame, and that's going to be 0. Wow. So if I add up all these and if I get a 0, then their dot with V center of mass in the ground frame is also 0. The third term vanishes. So the third term here will become a big 0. Very big 0 there. So what do I have now? The final result. So the final result is Ke of all the particles in the ground frame. So let me just make a note of it here. Ke of all the particles in ground frame is equal to Ke of all the particles in the center of mass frame plus half into total mass of the system times V center of mass square. And if you don't know the proof, if you know just this equation, then you will superficially think that this term shows you that the total mass is moving with the velocity of center of mass, and I will just take that square and maybe I'll have to find out this term. But now, because you know this entire proof, you know that there is a third term also that totally becomes 0, and that's how we end up with this entire expression, and which is actually pretty interesting. So this expression is worthy of being boxed here, and you should keep that in mind. Few things about this expression, you will see that I have not used any assumption. I have not said that there are internal forces between the particles, or I have not excluded those internal forces. So there may be internal forces, there may not be internal forces. That is immaterial. The masses m1, m2, m3, m4, mn, which I have assumed here, they may be discrete masses like this. So I have used it for a discrete mass system. But then if you have a huge mass and if you break it up into individual chunks, of course, what's the big difference between a body that is moving as one connected body and say discrete bodies? The difference is only that intermolecular force that one molecule applies on another molecule. So one particle applies on another particle. So if I keep that intermolecular force within the ambit of internal forces between these particles, then I can say that this result is true no matter what. So please keep in mind that result is independent of the nature of these masses. So these masses m1, m2, m3, these masses m1, m2, m3, up to mn may be a discrete masses, which means they are individual masses. They are not joined to each other, and maybe the only forces they exert on each other is when they hit each other, right? So the only forces will be collision forces. Or maybe they are joined to each other with strong intermolecular forces, and they have strong interactions between them, and they form something which is called a rigid body. So these masses m1, m2, m3, etc. up to mn may be a part of a rigid body, and maybe forming a rigid body, it doesn't matter. Or maybe in a more complicated case, they may be forming a deformable body. Whatever they are going to make, whatever is it that they are making up, this result is going to be true. And so this result will be used again and again by us, not just in this chapter, but in the next chapter also, which is about rigid body dynamics, where we will have a body undergoing some kind of rotational motion about a certain axis, and also translating maybe in three-dimensional space at the same time, and we want to maybe find out the total kinetic energy of the object in the ground frame. You can still break up that entire motion into two parts. In one part, you can think of the entire mass as being a particle that is traveling at velocity of center of mass, and in the second part, you can think of all those individual particles which are moving in some way in the center of mass frame, and then find out their kinetic energy. And this is a much easier term to find out than the K in the ground frame directly. So we will use this formula times and again in the next chapter, which is on rigid body dynamics. So please keep this in mind. Now, this will also find some application in the chapter which we are currently doing, which is system of particles, and the application is this. for a given velocity of center of mass. So let me ask you this question. For a given velocity of center of mass, that implies that V center of mass in the ground frame is a constant. So for a given velocity of center of mass, how should the particles move? How should the particles move such that their kinetic energy in the ground frame, in fact I'm saying ground frame, but it is any other inertial frame, so or any other inertial frame is minimum. And the answer to this is now very simple. Now you know that Ke in that inertial frame is going to be Ke in the center of mass frame plus half summation of m times V center of mass in that inertial frame whole square. And I know that this term is not going to be 0. This term is fixed. In fact, this entire term here is fixed. So I can only play around with the first term, Ke in the center of mass frame. And if all the particles are moving with the same velocity as the center of mass, so thing is, if V1 is equal to V2, in fact I should also say that this is V1 in the ground frame is equal to V2 in the ground frame is equal to V3 in the ground frame is equal to so on is equal to V center of mass. Automatically, if all the velocities are equal for all the particles, then the center of mass will be having that specific velocity only. So the last part is again, I don't need to say that, but I'm just explicitly mentioning it. So V1 in the ground frame is equal to V2 in the ground frame is equal to V3 in the ground frame is equal to for all the n particles, and you have is equal to V center of mass in the ground frame. Then V1 in the center of mass frame is equal to V2 in the center of mass frame is equal to V3 in the center of mass frame is equal to over all those n particles, and all that is 0, right? So that's let me say that this is equal to 0 in words, a greater impact there, and that means that Ke in the center of mass frame is going to be 0. Ke in the center of mass frame is going to be 0, and that will give you the least value of Ke inertial. In fact, since I'm using ground here, I should say ground, but this is true for any other inertial frame also. And if this was not true, if the particles were moving, then it will be immaterial whether they are moving forwards or backwards or wherever with respect to the center of mass, because in the end I will have to square their speeds, and there will be a contribution to this term that will not be negative, it will not be 0. So this contribution will obviously increase the total term on the right hand side, and the Ke in that inertial frame wherever you are standing will always be more than the case when all these particles were moving at the same velocity as the center of mass. So this is used a lot of times in spring block systems to find out the least kinetic energy of those two masses that are attached with the help of a spring, and if the total energy is going to be conserved, then the least energy in then the least kinetic energy will automatically give rise to maximum potential energy, and you can equate it to half kx square to get the maximum extension or the compression of the spring. So this is the theorem on kinetic energies, people.